everyone. My name is Enrique Kremers, and I'm presenting today about highly efficient and sustainable energy districts. So we are switching to the topic of energy in this presentation. I'm working at the European Institute for Energy Research. You see a quite highly loaded slide here for this introduction. It shows the complexity of this project that actually has been funded by the regional ministry of Baden-Württemberg in Germany, where we are located. And at the bottom, you see that this is a collaborative demonstration project. So we worked with a lot of practical partners together that were mainly implicated in the setup of this district and the construction of this district. Okay, so first, the motivation of our work and why to create a digital twin in this case. So we're talking here about the energy transition in Germany, which is a quite a particular landscape in the energetical world, I would say. So Germany's plan is to switch from coal and nuclear completely to renewables in the next decades. This implies a huge shift in the energy system. There will be the nuclear phase out end of this year and the coal phase out planned in 2038. The greenhouse gas emissions shall be reduced by over 55% against the targets of 90 to 2030. This means that today we have already in Germany installed a huge amount of renewables that change the way how the system is managed vastly because they are fluctuating. So we have solar 63 gigawatts and wind on and offshore 66 gigawatts installed. And you can see here as well the path of expansion that is quite huge. It's a bit small, but we expect in 2030 to almost duplicate these figures that are installed today. So it's a huge expansion plan that is being followed, and we have quite some challenges that are implied by this expansion. So mainly the problem here is how to integrate these new fluctuable renewable energies into the system. We have an electricity demand over a day that would look like this in an aggregated way. And the main problem is that in the future, we will have definitely more wind and sun, as we have seen, and they don't match this curve. Electricity has to be met immediately to cover the demand. So we can store it only in form of batteries that are quite expensive still for the amount of energy that we would need to store for a full district or a full city. So this is why in this project we follow the approach of using existing devices and their flexibility for actually better adapting the demand to the fluctuable renewables. This means, for example, shifting loads, so electricity devices that would run in this evening peak to run earlier when there is some wind and some sun available. So that is what we call actually flexibility. And if we do that in a proper way, the cost of flexibility will be much lower than the costs of installing additional batteries. So first, we have to activate as much as flexibility as possible. And then in the next step, of course, we can cover the rest of the energy demand that needs to be shifted with batteries. Why do we need what is called decentralized energy management? So in this shift towards a renewable system, here we have the classical system where we have the production on the top and on the down the demand. Yeah, and the only thing that actually was changing here is the production that is adapting continuously to the demand that is down here, and it is quite predictable and known, like the curve that we saw before. So here actually we don't need any special management. We just have a centralized management here that is adapting the power generation of this power plant to the demand that is aggregated at this point. However, if we look at the power system that is being currently set up and that will be set up also in the future more and more in this direction. We have a huge amount of new technologies entering the system. We have mainly photovoltaics and wind, but we also have new consumers on the electricity side, like electrical vehicles. And all these change the way how the system is managed and change also the flows. So we don't have just a unidirectional flow going from up to down, but we have many flows that are also injecting energy at lower levels of the power grid. This means that we have to manage all this system in a different way. And here decentralized energy management is the key word, because we will have to manage decentralized distribution, distributed generation resources. We have to manage distributed storage, and also we have to manage flexible loads, as for example, we were mentioning devices that can shift their energy use in time, like home appliances, for example. Okay. So in this project that is called Solar, that is located in Allensbach in the southern area of Germany, close to the Lake Constance, we are actually working on a real demonstrator, which is this district of 10 buildings, which includes around 25 households, in which we are currently setting up a decentralized energy management system. So here we accompanied the project since the beginning in 2018, and constructed in parallel a digital twin that we have the chance in this project actually to compare with the real demonstrator. So it's really a very practical project where we are in close link to the real system. So when we decided to build the virtual demonstrator, we actually had to evaluate the different characteristics of the system that had to be represented in the model. So actually we need a system that allows to control the collective swarm behavior that will emerge of this decentralized energy management, and which will lead to an optimized dispatching of flexibilities. So we are talking here about a complex energy system. You see there is a lot of controllable assets, more than 141, which includes the larger technologies like cogeneration plant and heat pumps, but also electric vehicle charging points, as well as the appliances, which are of course high in number, because you have washing machines, dryers, dishwashers, fridges, freezers, and all these for 23 households, which in total makes up around 141 devices that have to be represented. The devices are actually different in type, different in state, in time, of course, and they have to allow for autonomous and proactive decision processes at the local level. So we have high number of degrees of freedom, and also local constraints at these devices that we have to include in the model. We have also interactions between the entities, which are rather indirect, but that have also to be included. So to have a proper model representation that can capture the dynamics of the system, like for example the emergence at a higher level, we didn't find any commercial tool available that was considering these flexibilities in a proper way. And complexity science, so mainly agent-based modeling, brings actually a suitable approach that can allow us to represent this in the proper way. We have also to consider that we will have large data sets, and we need to manage all this data and analyze the simulation results properly. Here you see the setup of the demonstrator. We have multifamily households with photovoltaics, solar photovoltaics on the rooftop. There is a cogeneration unit that is supplying heat and electricity to this building, but also that is also supplying electricity to the single family houses that are here, that as well have photovoltaics on their rooftops, and that have a heat pump that is actually coupling the electricity to the heating system by producing heat out of electricity, so mainly using solar electric power to produce heat, to heat up the houses, and also to provide domestic hot water. So we see there is also this sector coupling, as it is named in the energy world today. So we have a coupling between the power sector, the heat sector, and also the cooling sector, if we take into account the cooling in the summer. Okay, so here we see already our virtual demonstrator in AnyLogic. So the virtual demonstrator is actually a mainly agent-based model that includes, of course, also some system dynamics and discrete event elements. It is a highly resolution model that is actually running at 1 second level. So every second we can have a decision and we can have a change of state of the devices. And we represent the different thermal and electrical flows at different levels. So from the appliance level up to the household level, up to the building level, and then for this full demonstrator level. So this is, let's say, a hierarchical agent model in which we embed agents into other agents and construct this model up to the top aggregation. So this 141 flexibilities. The thermal demand is represented with a physical model, so a so-called one-zone RC model for each household, and the electrical demand is represented with a load profile generator that gives us minutely profiles that are then interpolated at this second level and used to represent the different load curves, so it's the different electricity consumption curves of the different devices. For the generation, we also created some models to include the cogeneration plant, so the heat and power plant, and the photovoltaic systems that, for example, are included with the actual positioning and roof orientation. We can see some more details in the next slide about the model. So this is an example of a household that includes different parts that are modeled partially also as individual agents. So you can see here the electricity flows in yellow and the heat flows or the thermal flows in red. And you see that, for example, here there is a module that represents the water consumption that is linked to the person presence. That is then, of course, drawing some hot water from a heat storage. The heat storage again is connected to a heat pump, and so on. What is important here is that here we have the controller. So this is actually the controller that is allowing for the demand flexibility. So for shifting the consumption of the heat pump to the proper times with a autonomous algorithm that has been developed by a partner company of this project called Easy Market that is actually implementing this decentralized energy management system. So here the main decision are taken for our system, and this is connected to a grid state indicator that comes from the grid connection point. So we have actually a lot of agents, and they receive this information from the grid connection point and react with a decentralized algorithm that is included in each of the agents. Okay, so here we can see the model in AnyLogic, which is quite nice as of the representation. This is our virtual demonstrator. We see all the buildings here, and then we can see here different load curves. So the load at the grid connection point, which actually tells us how much is exchanged with the grid. Then we can go into the building level. Here you can see actually some load building and at the household level. So for example, here the photovoltaic production, you can see this is the heating system, a model with represented with system dynamics. And here, for example, you can see the temperature in the rooms of the buildings. Yeah? So and the state of charge of the storage, the temperature of the storage stored water. Also back here, we can see how the heat pumps actually will move in consume the solar power and with this increase the self-consumption of the site, so use better the local resources instead of importing a lot of electricity from the grid. Okay, so why do we call this a digital twin? So our virtual demonstrator is actually accompanying the project throughout the whole lifespan. So this is probably the most important difference to a traditional simulation model that is used on a punctual basis in one moment of the project when there is a punctual question that has to be clarified or solved. So here we're really accompanying the whole lifetime of the project with this model that has been set up in the planning and design phase, was already helping to plan and design this system from the beginning when there was not even any construction set. Then there was the construction phase, and during the commissioning, this model was also helping, for example, to fine-tune some parameters of the algorithm and to do already previous preliminary tests. We did as well tests in the lab in parallel to this energy system. So we had a lab in parallel where we did some hardware in the loop tests, so where the AnyLogic model helped actually to represent the virtual part that could not be tested in the lab. So in the lab, you can test, of course, the operation of one heat pump, but it's difficult to test 24 heat pumps, for example, and to test the 144 devices. So what we did was actually replacing these 140 devices by our model, and then connected a real heat pump in a hardware in the loop setup to the AnyLogic simulation. So that's a bit what we do with the digital twin. So the digital twin components that we actually consider are, of course, simulation models, spatial models that have been included also into DO 3D. Then we have the databases with all the IoT platform and the sensoring on the real side that actually is providing us the real load curves and the real production curves. So mainly the smart meters, but also some special measurements on different points of the system. And then we have, of course, all our toolbox of AnyLogic, where we can do some what-if analysis, some experiments, some parameter tunings to help to a better decision making. So, for example, to adjust some special parameters of this decentralized energy management algorithm. Last but not least, we have visualization. So you already saw the AnyLogic interface that is actually showing us the model in a quite a visual way. And then we have also infrastructure that helps us to evaluate and better analyze the results of the simulation. So let's have a look at some of our results. With this system, actually, we can increase the self-consumption rate. So this is the amount of energy that is self-consumed against the total produced energy on site. So the share of how much is actually consumed on site from the local production. This is something that with this system we can increase from 55% to more than 75% when we include different flexibilities. So in the first stage, we only include heat pumps and cogeneration, then we include the rest of the appliances, and then we include also electric vehicles. So we see how the self-consumption rate increases. Also at the same time, we have a reduction of the peak power, which means that we need less big transformers and less big cables at the connection point and in the power grid. So in this way, when you include the electric vehicles, especially, we have a huge reduction of this peak because we actually don't load them all at the same time and we shift the loading over time. All in all, so this increase of the self-consumption rate leads to a reduction of the operation costs of the system that is translated into a reduction of the electricity cost for the final users that can be up to 5 euro cents per kilowatt hour. So we have to say that in Germany, before, so this is all figures of before the energy crisis, was around 30 cents per kilowatt hour. So this is around almost 20% of savings in the electricity tariff. And of course, today we face a very special situation with the energy crisis and the limits of the Ukraine crisis that are affecting the gas imports in Germany. So electricity tariffs have gone up a lot, but we also expect that the savings are going up also proportionally. So this is something that we still have to do. We are evaluating it, but we expect that with higher electricity prices, of course, the savings will be also higher because in the end, what the self-consumption does is it reduces the dependency of the grid. So we actually reduce our costs by buying less electricity from gas power plants, for example. So if that cost is going up, of course we're saving more, and our local photovoltaic generation system is already installed there. So there we have stable costs. Okay, so here we can see a bit how the devices coordinate with each other in this decentralized energy management. So for example, you see here the curve of photovoltaic production, yeah, and these yellow curves, and the cogeneration that is actually producing electricity and power. So it doesn't make a lot of sense to produce electricity at the same time when we have some solar PV, because that will lead to feed into the grid back, yeah, that we have to buy again later at a higher price. Yeah. So what our system does here is shift the cogeneration to the moment when there is no sun. Yeah, so you see this brown curve is shifted to the morning and to the evening, covering the peaks of the demand, but not working at the same time than the photovoltaics. At the same time, the heat pumps that are electricity consumers should use the renewable electricity as much as possible. So here we see that random distribution of these heat pumps over the day is converted with the decentralized energy management algorithm to actually better behavior that is making use of the solar, the green solar electricity during the day. You can see the same effect here as well. Yeah, this is the heat pumps when they are working. Here you see very well how we have a sort of self-organization of the system, because these heat pumps have local decisions. They only sense the total electricity consumption, so that is expressed by this balance indicator, and they self-organize around these moments to make best use of the green renewable electricity without creating other peaks. And you see that the exchange with the grid, that is this blue curve, this is the balance indicator, is flattened. Yeah? And the more flat curve means that we have less exchange with the grid and we can reduce our local costs. Have a look at the appliances. So usually the appliances will work when they are switched on. Yeah, and here we have an operation window. So for example, people they tell us that they want their dishes washed at the next morning. So there's an operation window of a full night. And then again, like the heat pumps, these devices will switch to self-organize to not run all at the same time, but to run more or less sequentially, yeah, and then flattening the curve of electricity overall. Similar thing for the fridges. So the fridges usually run more or less homogeneously over the day. You see these red dots are the operation cycles of the fridges. Fridges are typically cycling. You might know that from when you actually are hearing the compressor of the fridge, so it's not working continuously. Then here they are actually switching the most suitable moments. Okay, a few words about the platform architecture that we use. So we have AnyLogic as a simulation core. We have some inputs that are mainly stored in Excel and in the AnyLogic database. Then we have also a versioning in the Git with a Git system. Yeah, that actually we use external to AnyLogic, but which works quite well. And we have the simulation web front end, so the AnyLogic Cloud that was used for visualization. Furthermore, we have this hardware in the loop export, so we export the model as a standalone, and then it can be used in other platforms as a jar file. Yeah. And for our data outputs, we mainly have a KPI file that is in a CSV format, which is storing a few important KPIs, key performance indicators. And then we have a huge amount of data because we have 200 time series, more or less. So the devices plus some aggregated time series, where each one is 31 million data points per year. So in total for these 200 time series, we have 6,000 million data points for one simulation. So these are quite huge numbers, several gigabytes, and they are handled with the InfluxDB, which is a special time series that can handle high amounts of data in the time series format quite efficiently. And then we use as a front end to actually analyze this data Grafana. We didn't do that in AnyLogic because we have so much data that is created after a year that we decided to do that as a post modeling exercise. Okay, then we can do exactly this post treatment, of course, in Excel that allows also not modelers to analyze the data. Just some short feedback before finishing from the simulator's perspective. So the approach used in this model was the agent-based approach, including discrete event and system dynamics that fits very well the complexity of the system. We also used the data-driven model. I didn't say a lot of that about that, but we have a database and we can customize the number of households, the number of devices via this database. So this is very important in order to make the model reusable. We had quite some important hardware requirements. So we had to shift from a normal laptop to a simulation computer that was a workstation with a higher amount of memory and with a bigger processor, but it was still, let's say, within a normal range. We didn't have to switch to a cloud platform completely. So we could do it on one PC. The platform complexity, actually, you saw it just before. So we have not only AnyLogic, but also this ecosystem. But the good thing is that actually AnyLogic is allowing this connectivity and is very open to connect to these different devices. So this is why it was really very very flexible in the way of connecting to the different bricks that we saw before. We also try to use the cloud, so which was a quite interesting exercise. We used it for some experiments and we also used it for some evaluation. But as I was saying, for this huge data that we generate, the dashboard was not yet ready. So we expect it also to evolve and to be probably more flexible in the future, so that we could also use more the cloud for these kind of projects. And as a short outlook, and I'm already finishing, we're actually going more towards a real interconnected digital twin. For the moment, we've worked a lot in this virtual world that you see here on the left, and we will do in the next steps more calibration with the real demonstrator, where we're currently getting more and more data because the commissioning was done end of last year. So we're now getting all this data. We want to do a real-time data interconnection and also add new functions, like for example replay function, so that you can replay a real historic scenario in your virtual world, do predictive control, do more optimization, and also include learning algorithms. So thank you very much for your attention, and feel free to ask any questions that you might have about this presentation. Okay, there are some questions in the chat that I'm seeing here. Okay. What were the main KPIs you have used to measure? So the main KPIs in these systems are the self-consumption rate, the peak power, both in the import and the export direction, the self-sufficiency rate, which is actually showing how much autarkic I am, so how much of my demand I can cover with this system, and also the economic indicator, so how much margin do I get when I do this decentralized energy management, so how much cents per kilowatt hour do I save on the final electricity tariff. How do you consider the grid and current flows in AnyLogic? We don't use the fluid library, no. We have not a specific grid model because we're not doing a power grid calculation here. Yeah, we are only working on power balance. So we just aggregate the load curves with a simple calculation in the model. Okay, this question I don't understand it completely. How do you use the model to make dynamic decisions about energy exports to the grid? Yes, so we are actually including some external data from the grid so that we can, for example, provide some flexibility to the outer grid. But this, of course, involves including some information about the power plants and about the energy market that is surrounding the system. Okay. Yeah, so the slowdown due to the system dynamics, I think that was a good point. We had to optimize the system dynamics to reduce it onto the minimum that we could accept, because of course, as the model size grows, as you are saying, we have actually quite calculations that are being done. So system dynamics, especially when you replicate it in agents many times, it is something that you have to do carefully. Okay, so I think we're through with the questions. Thank you very much, and then I let the floor to the next presenter.